All right, so we talked about our coordinates and position. Uh, the next thing to describe motion that we're going to need is the rate of change of position, which is velocity. I have here some plot of position as a function of time. The position is changing from like -5 meters, goes through the origin at 0, 2 meters, 3 meters. And at any point uh, along this curve, there's going to be a time and a position, one spatial dimension associated with it. So given this as a function, we talk about a few ways of describing and quantifying the motion. The easiest thing to start with is the one at the top. The average velocity is the displacement over a time interval. So it is the rate of change of position in the following sense. So it's like the slope of a chord. So if I picked T1 to be at 0, then X1 is -5. And then I could pick X2 to be here at 2 meters at a time of 4 seconds. So T2 would be equal to 4. And then I'm essentially laying down a ruler to connect those 2 points, those 2 space-time points. And the ratio of the displacement x2 minus x1 to t2 minus t1 is the average velocity. Just as the displacement does not capture everything about the motion, this average velocity is not capturing everything about how the particle is moving between those 2 times, t2 and t1. If I want something that is very precise at any one particular point in time, I can imagine shrinking T2 and T1 so they get closer and closer and closer together. And I can imagine at a limit that time interval delta t goes to 0, then I have the velocity. Technically, it's the instantaneous velocity, but we're going to use that so often as the velocity, we just drop the word instantaneous and just call it the velocity. The velocity is the first derivative of position with respect to time. So anywhere along this curve, when I want to know the velocity, I just pick that time and I imagine the tangent slope at that point. So the slope is positive all throughout this time interval from 0 up to 5 seconds, because the position is increasing with respect to time all throughout there. So at any point where I want to know the velocity, I go to the plot of position versus time. And at that time that I want the velocity, I just construct the tangent to the curve. And the slope of that tangent line is the velocity. So this is what calculus was invented for. The velocity is the first derivative of position with respect to time. So we talked about average velocity. When we do average velocity, I will actually write it out with AVG as a subscript to remind us that that is what we mean, average velocity. If it is just V without anything else, that's instantaneous velocity. We just mean velocity by and large. I won't say instantaneous. There is another construction that is sometimes useful. The average speed is the total distance over the total time, delta t. Let us do a question together. And this is taking one of these position versus time diagrams and connecting it to a story. So I have a person, it's initially at point P, stays there a moment, moves along the axis to Q, stays there a moment, then runs quickly to R, stays there a moment, then strolls slowly back to P. Which of those 6 position versus time graphs correctly represents this motion? So person starts at P, moves to Q, stays there a moment, runs quickly to R, stays there a moment, strolls slowly back to P. Which of those position versus time graphs describes that story? So think about it. If possible, talk it over with some neighbors. Pause the video before we go into the answer. So some of these plots I can immediately throw out because the person never moves left of the cube. So they could never cross the origin. So 1, 5, 3, and 6 are all out because those are all cases where the person reaches or crosses the origin. So it can't be any of those. Now, the 2 survivors, we look at 4 and 2. In 4, in moving from Q to R, that is a shallower slope. And then from R to P is a steeper slope. So 4 is describing a stroll, then run. For 2, we are looking at the person runs from Q to R because it is a steep slope, and then a shallow slope as they go from R to P. And that is the one that actually matches our story. So runs quickly to R and then strolls slowly back to P. The one that matches our story is the graph 2, position versus time. And then notice if you're not changing position, so you stay there for a moment, that means your position is constant as time evolves. So you just have a horizontal line in a position versus time graph.